All right, we are going to skip 8.3, so do not do 8.3, and we're going to go to 8.4, two pools. To prepare for a backyard party, a parent uses two identical hoses to fill a small pool that is 15 inches deep and a large pool that is 27 inches deep. The height of the water in each pool is a function of time since the water is turned on. All right, so they're saying that we use two identical hoses, I imagine, to let us know that they're both gonna, be filling up at the same rate. Like they're gonna both maybe have, a gallon of water per minute each added to the pool. Right, if you're doing an experiment and you're doing an experiment on two different groups, you want to make sure you're using the same constraints, the same constraints on the experiment. All right, so let's see what we got to do here. All right, here are descriptions of three situations. For each situation, sketch the graph of the two functions on the same coordinate plane, so that S of t is the height of the water in the small pool after t minutes, and L of t is the height of water in the large pool after t minutes. So that means I'm going to need two colors. Let's say S of t. We're going to do that in pencil. And let's do, where's my purple pen? Let's do L of t in purple. All right. So keyword here is they say we're doing a sketch. So no need for graph paper here. If you're someone who doesn't print these out, you can just use normal paper and do a rough sketch of your X and Y axis, although I would use a straight edge. But we're not using graph paper here, it's just a sketch. So situation one, each hose fills one pool at a constant rate. When the small pool is full, the water for that hose is shut off. The other hose keeps filling the larger pool until it is full. All right. So we kind of have to make some assumptions here. And I'm going to assume for this that that the small pool is only going to take 10 minutes. 10 minutes to fill. Or let's say 8 minutes. I'm going to assume it takes 8 minutes to fill. So that means that if the small pool, if we look back here, the small pool is 15 inches deep. That means after 8 minutes, I should be perfectly at 15. So 50, this is 12, and this is 18. In between those is going to be 15, right? Plus 3, plus 3. So that means I'm going to be perfectly at 15 after 8 minutes for the small pool. All right, once we get to the full volume, they're going to turn the hose off, so that height is going to stay the same. All right, now let's see the large pool. So if they're being filled at the same rate, the large pool is actually going to stay exactly in line with the small pool. We're also assuming that they're the same size, just for easiness sake. All right, so now we see that we have to get all the way up to 27. So I know 27 is going to be right in between here. So we're going to get at 27. Let's say we get there at about, maybe let's say 15 minutes. So here's 14. So 15 is right about here. And again, you can really, as long as you can justify it, you can really estimate it however you like. All right, so once it gets to the full amount, it's going to flatten out. So that would be my example for the two pools being filled up. They're both being filled at the same rate, because they say each one fills the pool at a constant rate, and it's the same amount. You could argue that because this one is wider, it's gonna take a much longer time. But for this one, I'm just gonna assume, since they said it's the same rate for each hose, that it's gonna look constant. It's gonna look the same here. All right. Situation two: each hose fills one pool at a constant rate. When the small pool is full, both hoses are shut off. So in that situation, the small pool would actually just look the same. That would be the same where we'd get that same graph as before. And then for the large pool, it would also just be the same as the small pool, because we're filling it up. And then once the small pool is full, both hoses are shut off. So this one is not getting any higher up. All right, situation 3. Each hose fills one pool at a constant rate. When the small pool is full, both hoses are used to fill the large until it is full. So again, the small is really going to stay the same for all 3 of these. Nothing has changed for the small pool. Now for the large pool, it's going to stay the same as the small pool. But then once the small pool is full right here, we're going to have 2 hoses. So my rate of change is going to be doubled. So in this one, it looks like we said it was about 2 inches per minute. Since I'm at 15 and that's 8 minutes, it's a little bit less than 2, but it's around 2. So it's going to be more like 4 inches per minute now for the large pool. And remember, this is a sketch, so I'm not being incredibly accurate. But if we look here in my original, we said it was at like 15 minutes it took to fill. And so here it's 15 minutes, and we started here at 8 minutes. From 8 to 15 is 7 minutes. So if I'm using 2 hoses, I'm going to fill it twice as fast. So instead of filling it in 7 minutes, or I'm going to fill it in half the time, it's going to take 3.5 minutes. So that means I'm going to get to about 11.5, because if I add 3.5 to 8, I'm at 11.5. So that's right about here. And we're going to get to 27. So those intersect right there. So then the large pool will be full a lot quicker, and then it will remain flat. And of course, your graphs might look a little bit different. You just have to be able to justify it, right? This is a sketch. It's not written in stone. As long as you can justify why your graph looks a certain way based on the situation and your interpretation of the situation, that's fine. All right, and that is all for 8.4. You are not required to do 8.5, so you can cross that one out. No need to do 8.5. So you can just start the homework now. All right, have a good day.